Last time we looked at the working of the buck converter, which is used to decrease the input voltage. In this video, we will look at the working of the boost converter. It is used to increase the input voltage. In a buck converter, the voltage is reduced by increasing the current. Similarly, in the boost converter, the voltage will be increased by reducing the current. Both the converters use the same components but in different arrangements. This is an N-channel MOSFET. It is controlled by the PWM signal. When the switch turns on, the current starts flowing in this loop through the inductor. As current through an inductor cannot change instantly, thus current increases gradually. Also, the inductor starts storing this energy in its magnetic fields. In this circuit, the switch has zero resistance. Also, you would know that the inductor acts as short circuit for DC. Thus the current through the inductor can increase to the maximum amount that the source can provide. For an ideal source, the current will increase to infinity. Now, as the switch turns off, the current will flow through the larger loop. But the current is too high for this load at 5 volts, and the current will not change instantly. Thus inductor increases the voltage such that the combined voltage of the inductor and battery can flow this current through the load. The inductor runs out of energy pretty soon, and this gives a large spike of voltage at the output. So now we can increase the voltage at the output than the input. But it's not continuous. Hence we add a capacitor, parallel to the load, to store the energy in the spike and then release it later. But something weird seems to happen. When the switch turns on, the inductor charges. And, when the switch turns off, the inductor discharges, charging the capacitor. Now, when the switch turns on again, the inductor charges but the capacitor discharges itself through the switch and almost no current flows through the load. Hence, we add a diode between the inductor and capacitor so the current can flow only in one direction. Now when the switch is off, the capacitor charges by the inductor, and when the switch turns on, it discharges through the load, thus keeping a constant supply of current and voltage at the output. And the boost converter is complete. If you increase the duty cycle of PWM, the voltage increases, and if you decrease the duty cycle, the voltage also decreases. But, similar to the buck converter, it has the same problem. That is, as the load changes, the voltage at the output also changes, depending upon how much current the load draws. Hence, we add the feedback voltage divider, the op-amps, and the triangle wave generator. In this circuit, we use an N-channel MOSFET. Hence, the inputs of the comparator are flipped. All other working principles remain the same as the buck converter. Any changes in load will change the voltage at the output. This will change the feedback voltage, thus it will change the duty cycle of the PWM. Also, the voltage can be changed by adjusting the potentiometer. While designing this, some care should be taken. First, the output voltage is higher than the input and it can also reach above hundreds of volts with a 5-volt battery if the duty cycle is increased too much. Hence, be careful while using this circuit. Second, check the breakdown voltage of the diode. It should be higher than the maximum voltage at the output or the diode can get damaged. Now, what if you want to increase and decrease the voltage with one device? Can we combine both of them in one? Yes, you can. And, such a device exists. It is called a buck boost converter. Here we combine the buck and boost converter in series. Then remove this extra capacitor and combine the two inductors in series to make the buck boost converter. Now, when the second switch is off, this acts as a buck converter controlled by the PWM at the first switch. And, when the first switch is on, this acts as a boost converter controlled by the PWM at the second switch. Rather than controlling two switches, there also exists another configuration of the buck boost converter. It is known as the inverted buck boost converter, and operated with one switch. This can obtain voltages from 0 to below -100 volts with a voltage source of 5 volts. Why negative voltage? Let's see. When the switch turns on, the current flows through the inductor in this loop. It cannot flow to the other loop because this diode is reverse biased. Now, when the switch turns off, this loop is now open, hence the current flows through the other loop. This terminal is connected to the ground, hence it will always be at 0 volts. Now, if the inductor wants to continue the flow of the current in this direction, the other terminal must become negative. This terminal of diode is negative and this is at the ground or 0 volts, thus the diode is now forward biased, and this is a close loop for current flow. You may know that the current flows from the higher potential to the lower potential. Here it flows in this direction, and this is at 0 volts, thus the other terminal is at the negative potential. Also, the capacitor gets charged in similar polarity. Now, when the switch turns on again, this loop closes and the diode is again reversed biased. During this phase, the current through the load is provided by the capacitor. If you decrease the duty cycle of PWM, the potential difference decreases, and if you increase the duty cycle, the potential difference also increases. This is how the boost and buck boost converter works. Thank you for watching and continue by watching our other videos.